This is section 3.3, Rates of Change in the Natural and Social Sciences. And our first objective is to apply the concepts of average and instantaneous rates of change to motion problems. And you probably recognize this objective because we've been working on it since the very beginning of the year. But now we've got some new vocabulary to go with this that we're going to reiterate and then add some more. So first we have the position function. Usually this is denoted by x of t, y of t, or s of t. And the position function, what you need to remember about it is that it always tells where an object is. It gives the location at any time. Then we have what's called the displacement. So the displacement of an object over a time interval will be the net change in the position of an object. It will tell the difference between the initial position and the final position and will be where we end up minus where we started. Instantaneous velocity, as you know, is the derivative of the position curve. So now we can write v of t is s prime of t. This velocity function will tell how an object is moving. So when an object is moving up or to the right, the velocity will be positive. When an object is moving down or to the left, its velocity will be negative. When an object is at rest, the velocity is 0. And lastly, in order for an object to change direction, the velocity has to change sign. So that means that the graph of the velocity would have to cross the t-axis. Now we've got a new vocabulary called speed. And velocity has both magnitude and direction. Remember, it tells you how fast you're going and the direction in which you're traveling. Whereas speed is just the magnitude. It only tells you how fast you're going instead of giving you the direction. So if we want to strip off the direction and just talk about how fast we're going, we will take the absolute value of the velocity. Next one that is new is this instantaneous acceleration. So the acceleration is the derivative of the velocity curve. So that means it will be the second derivative of the position curve. The acceleration, unlike the position and the velocity, it will not tell you where you are or how you are moving. Instead, it tells the push on an object. So when acceleration is positive, the object is being pushed up or right. When acceleration is negative, the object is being pushed down or left. So when acceleration is 0, that's like your foot is not on the gas or the brake. You're not going to be pushed at all, and you will merely coast. So what does this mean for us in terms of problems? If we look at example 1, it says if a ball is given a push down a certain inclined plane so that its initial velocity is 5 meters per second, then the distance it rolls after t seconds is going to be given by this position function. So the first thing that we want to do is find the velocity after 2 seconds. So we need to remember that the velocity is the derivative of the position, which will be 5 plus 6t. So if I want the velocity after 2 seconds, then that will be a 5 plus a 6 times 2, which is a 12 plus a 5, or a 17 meters per second. Next part, how long does it take for the velocity to reach 35? So in this case, we know what we want the velocity to be. So that velocity, which is 5 plus 6t, needs to equal 35. If I solve for t, I will get t is 5 seconds. Next part says, what is the acceleration at any time? So remember that acceleration is the derivative of that velocity function, or the second derivative of the position. So we go back to our velocity function and we take the derivative, we get a positive 6. Now the units on acceleration will be meters per second squared, because if we think about the slope of the velocity curve, with velocity we were putting time in and we were getting meters per second out. So a slope, which would be a rise over a run, would be a meters per second over a second. So that 2 seconds on the bottom would give us the second squared. Example 2 is a numerical example where again we are given the position and asked questions about it. So in this case we have a chart of data that tells us that our position at these times is given by these numbers. So if I want to estimate the instantaneous velocity at 1 second, then I'm going to locate the 1 and then do the flanking points. So my flanking points, y minus y over x minus x, will give us an 18 over a 1. If I measure the units, remember position is measured in feet and time was measured in seconds. Again, if I want the velocity at 2.5, I will use my flanking points to find the slope. So I locate the 2.5, go left and right. I'll have a 48.5 minus a 48.5 over a 3 minus a 2. So in this case, I'm going to end up with 0 feet per second. Part B says, on what time interval does it appear that the velocity is positive? Well, the velocity will be positive when these slopes are positive. So when the y minus the y over the x minus the x gives us a positive output. We can see that by looking at the y values themselves to see if they are increasing. Because if these are getting larger as t gets larger, that means the graph is increasing and we'll have positive slopes. So here our position is going up, and it continues to climb until 50, and then it starts to go down. So that means we are going to have positive velocity until 2.5. So we can write the time interval from 0 to 2.5, and we don't include the 2.5 because it appears at that point we're turning around. With example 3, we have a particle moving along a horizontal wire according to this law of motion. So first part, we want to find the velocity at any time. So velocity, if you recall, is the position of, or the derivative of the position. So we get a 2t minus 10. The next question asks when the particle is moving to the left and to the right and when it's stopping. So remember that velocity is what tells you how you're moving. So to figure out when we move left and right, we need to look at when v equals 0. V is going to equal 0 when time is 5. So now we can recall our old Algebra 2 techniques, where that s prime of t or perhaps v of t, and we can do a number line analysis of what's happening prior to 5 and after 5. So prior to 5, I have numbers that are smaller than 5, so that'd be like a 4. I end up with a negative number. And after 5, say at 6, I end up with a positive number. So I can see that prior to 5, I have a negative velocity, and after 5, I have a positive velocity. So the particle will move to the left as long as t is less than 5. The particle will move to the right as long as t is greater than 5. Now the next part says, where is the particle the first time it stops? So this word where should be telling you that you need s of something, because remember that position tells you where you are, and we want to know where we are the first time it stops. So we see up here that we're stopping when the velocity is 0. So we will be computing s of 5. If I plug 5 in, I get a 25 minus a 50 plus a 12. So that's 25 minus 50 is a negative 25 plus a 12 gives me a negative 13. Part E says I want to find the displacement over the first 8 seconds. So that means I want to know where I end up minus where I started. If I plug 8 into the function, I get a 64 minus an 80 plus a 12. Well, that's a 76 minus an 80 gives me a negative 4. And then I'm going to subtract s of 0, which means I plug zeros in here and I get a 12. So if I have a negative 4 minus 12, I get a negative 16. What this means for you in context is that we are now 16 units further to the left than when we started. Part F is where it gets a little tricky. So we want to draw a diagram to illustrate the motion of this particle. So the particle is going to start at s of 0, which is 12. So if we draw our number line here, we're going to start at positive 12. And we are going to start moving to the left, because as long as t is less than 5, we have to move to the left. So we'll start here and we'll move to the left until we stop. And we're going to stop when time is 5. So I'm going to put a little t equals 0 here. and at t equals 5 is when I have stopped. Now notice when I plugged 5 in, I was at a negative 13. So now, once I stop, then I start to move to the right. So we're going to turn around and head the other direction until time, which is 8, when I land at negative 4. So at negative 4, my time is now 8, and I have stopped my counter at negative 4. Time is negative 4. So here's a diagram that would illustrate the motion of the particle. So I would do S of t here, and we're going to keep moving to the left, or to the right, excuse me, for the rest of the time. So G says I want to find the total distance that was traveled by the particle during the first 8 seconds. So we started at 12, we went all the way down to negative 13, so that's 25 units already, and then we're going to add on another 9. So we end up traveling 33 units, even though where I started versus where I ended had only a 16 unit difference. With example 4, we're dealing with a rock that's thrown vertically upward from the surface of the moon, and we can model the height with this function h of t. So the first thing we want to do is find the rock's velocity and acceleration as functions of time. So the velocity will be the derivative of that position function, which is 24 minus 1.6 t, and the acceleration will be the derivative of the velocity, or the second derivative of the position, which will give us a negative 1.6. Now we can talk about the units. Velocity is meters per second, and acceleration will be meters per second squared. Part B says, how long did it take the rock to reach its highest point? So there's a lot buried in this problem. When we're done, we want a time, and we want the time when the rock is at its highest point. So if you think about what's happening with the rock, it's going to go up, and then it's going to come down. So what do we know at that highest point? We don't know what the height is yet, but we do know that it will have a horizontal tangent line. So what we're going to be doing is we're going to solve for when that velocity function is 0, and we want to make sure that we look for a time that is greater than 0. So I'm going to pull out the calculator so you can see how that works. And in the calculator, I have put the position function in y1, the derivative or the velocity in y2, and the second derivative or the acceleration in y3. So if I want to solve for when the velocity is 0, I'm looking for when this y2 is 0. So we'll go to the home screen, and we're going to hit F2, and we're going to solve for when y2 of x equals 0 with respect to x, and then we want to make sure that we're looking for when x is positive. So if I hit enter now, I get a time of 15. So we know that the time that it took to reach the highest point is 15 seconds. Now the next question asks, how high did the rock go? So this is asking for an output of the position function. So we're looking for an output on the position. Well, we know the inputs for position are time, and the time that we just found in part B was how long it took to get to that highest point. So we're going to plug 15 into h, and remember we stored h in y1. So back to our calculator, and we can go to our y1 and plug in a 15. Hit enter, and we get 180 meters. So back here, we can now write 180 meters. Next question is, when did the rock reach half its maximum height? So this is going to be asking us to find a time, and we know the height is half of this 180. So we're going to solve for when h of t equals half of that height. So back on our calculators, we will solve for when the position, remember that was in y1, is 90, and we're solving with respect to x. I'll do a diamond enter here just in case, because I don't want to get some radicals. And I see a 25.606 and then a 4.393. So we're going to put those down. 4.393 and what was that, a 25.607. I'm going to round up. So back here on when did it reach its maximum height, we have 2 times, or half of its maximum height. We get once on the way up, and we get another time when we're on our way down. If we go to this little model here, that full height was 180, and we're going to our half that height at these 2 time periods, or 2 times. Last question is, how long was the rock aloft? Well, when we are no longer aloft, then we have hit the ground. So our height is going to be 0. So again, we're going to solve for when y1 of x equals 0, and we want to make sure that we look for time that is bigger than 0. So back to our calculator, we're going to solve and just change that 90 to a 0. And then we're going to limit our hunt to values of x that are positive. Hit enter, and we get 30 seconds. Now notice that this makes sense because it took us 15 seconds to get to the top. It'll take us another 15 seconds to get down because of the symmetry of this position curve. With example 5, we are given information graphically. So we've got a picture of the velocity, and it shows the body that's moving along the x-axis for any time t. So the first thing we want to do is graph the speed. And the speed, if you recall, strips the velocity of its direction. So it's the absolute value of our picture. So graphically, that's going to take anything that's underneath and pop it to the top. So we'll have this picture, and then what's underneath gets popped up. A little bit shaky, guys. I'm bad at this. Drawing straight lines is a little rough. Then up to here, and down to the 10. Hopefully the one in your notes will look a little better than what I have sketched out here. So here's our speed. Next we want the acceleration. Well, the acceleration is the derivative of the velocity, or the slope. So here we can see that between 0 and 1 our slope was 3. So we'll go from 0 to 1 with a slope of 3. Notice that I have an open circle at 1 because I've hit a corner on the velocity graph, and I can't get a derivative at the corner. Now my slope is -3 because I've gone down 1 and over, or down 3 and over 1. So again, I'm at a corner, and I get to stay at a slope of -3 until time 3. At time 3, now I flatten out, so my slope is 0. So that means I'm coasting and there is no push until 6. Then at 6, I pick up, I start to push again, so now I'm going to have a +3, and I stay there until 8. And then after 8, I have a -3/2. I can close the ends because these ends are not corners. I only have to get a slope from one side since they're the endpoints of our domain. So the question C says, when does the body reverse direction? Remember, direction comes from the velocity curve. So we're going to be looking for when the velocity changes sign. Velocity is going to change sign at 2 and again at 7. When are we moving at a constant speed? That's when we don't have any push, or when the speed is not changing. So we can see it here from 3 to 6. The object will speed up. Now here's where it gets a little tricky, because you need to think about when you actually speed up. If I'm moving to the right and I'm pushing to the right, then I'm going to speed up. If I'm moving to the left and I'm pushing left, then I will also speed up. So we got to think about how this is manifested graphically. If we look at our speed, the speed will be increasing when we have positive slope on the speed graph. So that goes from 0 until 1, and then again from 2 to 3, and then again from 7 to 8. And how would we see that on the original? Well, from 0 to 1, we have positive velocity and positive slope. From 2 to 3, we have negative velocity and negative slope. And from 7 to 8, we have positive velocity and positive slope. So we can make the same argument for when we are slowing down. We're going to slow down when the speed has a negative slope, which is from 1 to 2, and then again from 6 to 7, and then again from 8 to 10. And we can see that on the original graph of the velocity by looking for a negative slope when the velocity is positive, or a positive slope when the velocity is negative, and again a negative slope when the velocity is positive. You have some notes, web exam problems to work on now, and when you're done, I'd like you to explain the relationship between velocity and acceleration when an object is speeding up versus slowing down.